okay, back to the question just now, how do you decide on the mutation? All right, so first and foremost, of course, you're not going to do too much mutation. So in this case, let's say we decide we want to do only 1% mutation. Okay, kita tak nak buat banyak lah, just 1% mutation. So 1% mutation is then 0.01 mutation. So since you have 300, so you have one chromosome is having 33 bits, remember? So you have 10 chromosome, so you have 330 bits. So when you decide 1%, it means you expect 3.3 mutation per generation. So in that generation, of course, you're going to have 3.3 mutation. You're going to have 4 lah. Okay, maximum, the nearest number is 4. So you're going to have 4 mutation in this example. Okay, so that because of the mutation rate that you have decided. Is that okay? Is that okay for that point? Okay, then when you decided that,
Okay.
all right, so when decided that, you then will select what we call, we generate 330 random numbers in range of 0 and 1. Okay, so you select 330 random numbers in 0 and 1. Okay, and let's say this is the random number you have selected. Okay, that is the random number you have selected. Okay, so from that random number, you convert back to you convert to the bits number, to the bit. Okay, so change that into number. Okay, when you change that into number, it will give you your bit position. Okay, so when you get your bits position, katakanlah bits dia tu 105. Ni dia sebenarnya ada I think there's something I miss here. Okay, there's a way to convert from this random number to bit position, but I think I missed that information in this slide. That's why you have queries, I think. Okay, so I'll check again if there's any missing information. How do we convert from 0.099 to 105? Okay, I will let you know later. Okay, let me check back the notes. Okay, I think I missed some information there. All right, so basically when you have that random number, you can convert to the bit position by having this actual number. So with that actual number, we look again what does it display. So if you know that the first chromosome is having 33, right, bits, okay, the second chromosome will be 66. So this is actually 34 until 66. And then this will be 67 until 99. And then this will be 100, okay? So 104 and 105 is actually relies on chromosome 4 and bits number 6, because this is 100, 100, 101, 102, 103, 104, 105. Okay, so 105 will be your bit number 6. Okay, so then that value, instead of 1, it will become, when you mutate, you become 0. Okay, and then similarly for the rest. So for in this case, let's say your bits that you selected is 164. So 164, this is actually by roulette wheel as well. I think I missed one information about roulette wheel. We did the selection based on just a random selection, basically, to answer your question. Okay, but the number of selection we decided for. Okay, so you just macam like you toss a coin lah, just to check which one you want to do mutation. So it's completely random. Okay, so in this case, I think I missed one selection on the roulette wheel selections. So that's why it seems quite jump from one numbers to another. So how do we convert from that random number to the bit position? Okay, so using roulette wheel again. All right, so then similarly for chromosome number 5, it is 164. So 164 is lies on chromosome 5, bit number 32. So chromosome 5, bit number 32 is this one. Okay, so from that 1, it becomes 0. You just convert it into 0. So that, if you look at binary as if it is a very simple conversion, just from 1 to become 0, isn't it? But if you convert that to decimal, it is something completely different. And in fact, if you convert from decimal to real number, it becomes quite different, very distinctively different from the previous value. Okay, so similarly you will do for your chromosome number 7, bit number 1, and chromosome number 10, bit number 32. That's how we do our mutation. Okay, but basically the choice of which chromosome and which bit to be mutated is completely random. you just select your percentage of mutation, in this case 1%, and then your computer will actually randomly select the numbers to be mutated. It's not up to you to decide actually, it's just randomly selected. So a computer will do the selections, okay, without any knowledge on that. So nothing to do, nothing to reserve or anything, no. Okay, it randomly selected. Just like in our population, in human population. So when you select one children to be completely different than the other, it's not your decision which one, isn't it? It's decided by the Almighty, isn't it? So similar in this algorithm, the decision is not on your hand, it is decided by the computer, randomly selected. Okay, so in this case, I think I missed one information from this value. How do we create roulette wheel selection? Okay, using roulette. How do you spell roulette wheel? Roulette wheel is like your you just toss a coin, or just you know that roulette wheel, the one that in the Wheel of Fortune, isn't it? We just make it twist, okay, and then when it goes in the round and round, it will start at one point. That's it. Then you choose that point. So it's completely random. Okay, is that all right? Is that answering your questions?
Yes.
Okay, then when it become mutated, okay, let me just focus again on mutation and also crossover. For genetic algorithm that you need to remember, the first one is crossover. Let's say crossover is as simple as this. Let's say I have the chromosome is 110, and then the second chromosome that I want to cross it over is maybe 010, 011. Okay, so when you decide to do the crossover between these two chromosomes, this chromosome is known as parent. So this is parent 1, this is parent 2. Parent is like mother and father lah. Okay, then when you want to do crossover, the location to do the crossover also completely random. You can toss a coin and decide and ask the computer to select randomly which is the position to do the crossover. Okay, so let's say it is decided on the second chromosome. Okay, so when it is decided on the second chromosome, you will see that you will breed a new population, the new offspring. We call it offspring like children, okay? The new offspring, the first one will carry the head of the first parent, okay, and the tail of the second parent, okay, so 0, 0, 1, 1. So you can see that this number 1, is completely different than the parents, both of the parents, okay. So this is called offspring 1. Okay, similarly for the second one will carry the head of the parent, the second parent, but the tail of the first parents. Okay, so 0, 1, 1, 1. So you can see it is now the second offspring 2. We call it just offspring 2. So both of them are now completely different between one another. Okay, so then what we are hoping by doing this crossover, okay, when we do the crossover, what we hope is that these features from your parents one will give you a better when it is converted to your offspring 1 and 2. Okay, so this one is actually now is here. So that breed you will give you a better performance, or on if it's not better, you want to actually try and error find a new region of search. Okay, like I mentioned just now, when you create genetic algorithms, this is what you do. You do the random search on your search area. Let's say this is your search area and your objective is to find the minimum value. And let's say your minimum value is, this is local minimum, this is global minimum, another local minimum, another local minimum. If you're using calculus, okay, so probably you already stop there, okay, if you're using calculus, right, and then you will never proceed. But because you're using genetic algorithms, you are using overall search, so you create agent. Let's say your agent failed to find to be a place on this first on the global minimum in the first place. So your agent are all scattered, but not in the global minimum for one reason. Okay, so because this is completely random, isn't it? So what happened is that when you evaluate the performance, you will see that you will thought that the performance is in this second you thought you will think of that maybe it is around here, the minimum, because there is the both of the value uh, what do I say, apa ni, close to one another, and then that value also the minimum from the rest of the values, isn't it? So you might thought of that. So if you create chromosome by just doing ranking and then without doing any crossover and mutation, your next cycle of genetic algorithm, the next cycle, let's say I give you a different color, okay, the next cycle, your next 10 chromosome will lies in this area alone. You will scan this area alone, okay. So that is why you do not want to stuck at that area, okay. So you want to one of them maybe to be changed completely from the offspring. So this can happen by creating mutation and crossover, hoping that when you have mutation you create a completely different value, that it might goes there, okay. Or maybe it's not even there, maybe it's somewhere far and the performance is even worse, like what you've seen just now, isn't it? You create a crossover and mutation from the example, and one of them is performing really bad. So it's not really, it doesn't mean that the offspring is better than the parent, but that is what we're hoping to have, okay. It is actually completely different, so that maybe if it's not within the area that we are searching, it can actually drop or fall on a different area where your minimum will be. So if your minimum is found in the next generation, so the third generation, all your offspring will be actually focused on the new minimum, okay. So all your 10 offspring will be focused in this area now. So you will forget all the red area and the green area. You will focus on now the new apa ni, where your new minimum lies, and then all the 10 genes or chromosome will be scattered around this area, and perhaps one of them will find the minimum value, which is this case is there, okay. So that one of your chromosome will found the minimum value. So third generation, your GA is already converged to the minimum value that you want, okay. So this is how your genetic algorithms works in terms of crossover and in terms of your mutation. Mutation is as simple as this. Let me just show mutation. Okay, so mutation is as simple as, for example, mutation doesn't need parents, okay. Only crossover need parent. Mutation can be mutated by itself. So just from the example that I showed just now, okay. So if, for example, the value is 0 1 0 1 1 1 0, okay. So when we do mutation, let's say one of them is selected to be mutated in this area here, okay, that one bit can be mutated. So what happens is that your new chromosome will be 1 1 1 1 1 0. In terms of a binary, it doesn't look many difference, isn't it? It doesn't have a lot of difference, isn't it? But in terms of decimal number, and also when you do your decoding, it will actually create completely new numbers, okay, compared to the previous one. All right. Is that okay for me? Mutation and crossover for your GA. Okay, so is that all right? Okay, in terms of your applications, all right. Last time you remember you have your recursive list. I want to show the MATLAB programming, but unfortunately my license is UTM's license. I cannot utilize it using my Wi-Fi. I have to use UTM Wi-Fi, so I cannot open the optimization. And in fact, the one that I opened just now, there's no longer there. The genetic algorithm is no longer there. You know, sometimes toolbox, the genetic algorithms toolboxes, they have lifetime. Okay, so sometimes the lifetime, the duration of the license is 10 years, 20 years. And after that time, it will disappear from MATLAB. So the new version of MATLAB you bought might not have the previous license toolbox. So I think that is why the reason why the one that I have is the latest one. So this one doesn't have the toolbox of MATLAB. And I tried to use the UTM's one, it cannot because it detect my Wi-Fi is not from UTM. Okay, so that's the problem. But anyway, I want to show you what happened when we have GA to do optimization of our parameters. So remember last time we have our least squared and recursive least squared. It is the same, you know. So when you have your least squared, okay, your least squared from least squared is coming from ARCS model. Okay, so your ARCS model, you said that your system is having, your system is having a parameter of B over A. Okay, this is your output over input. It is a parameter of B over A where it is an ARCS model, let's say with model order 1. Okay. Okay, so this is ARCS model with parameter 1. So what you want your GA to find is the combination of B1 and A1. Similar like your least square, you want your GA also to optimize this value so that you have the best value so that your predicted error is the lowest error. So what you want to do is that you want to put this in a loop of GA, okay, asking the genetic algorithms loop, okay, for loops, okay, where within that you're going to write down the Y, your equations. Okay, let's say before that, before you have your loops, you want to write this down in terms of your Y. So you're going to have Y1 plus A1Z minus 1 is equals to, this is multiplied by U, isn't it? Okay, is equals to BZ minus 1 multiplied by UK. Okay, so this is your YK, right? So then you're going to have your, again, you have going to have your YK is equals to your negative A1 YK minus 1 plus B1 UK minus 1. Okay, so this is what you have from your ARCS model. And then what you're going to do is actually you're going to put this in your MATLAB, in your programming. Your GA will optimize that. And then your cost function is you're going to put A in terms of A and A1 and B1 in terms of binary. Okay, so you're going to find out what is the best, what is the range of parameter for A1 and what is the range parameter of B1. If it's unknown, you can just have a guess. Okay, if it's unknown, you can just say that, okay, A1 is in between certain value into certain value by just having a guess out of it. So because you do not know the actual value, isn't it? So you can put the range maybe from negative 100 until, if you do not know. If you know, then of course you can put the value that you can put that like that, okay, if you do not know. And then similarly for B. All right, so from there you can, so you mean to say, you know that within, if this is the range, this is really big, okay, the search area is really big. So maybe your chromosome, 10 chromosome is not enough. Maybe you want to create 50 or 30 or even 100 chromosome within one generation. Okay, so for your A and B, then you convert this value into a binary numbers, and then you convert it into a population. So you have your population, populations. Oops. You said your populations of equals to 100, and then definitely then you're going to generate GA, okay, with the V1 until V100. You're going to generate it randomly. Okay, random, and it is in binary. And then you immediately will use, you convert this. This is the first one, you generate the population. The second one, you will, of course, you will actually evaluate the performance of your chromosome, V1 until 100. You're going to evaluate the performance. How do you evaluate the performance? Is by converting the chromosome V1 until 100 chromosome, okay, all these chromosome, you will convert it into your combinations of A1 and B1, and of course, how many combination you have? You're going to have 100 pair of A1 and B1. This is if it's model order 2. You mind you, for GA you can do model order up to whatever you like. Okay, you can have it model order 2, 3, 4, 10, even higher order. Okay, and it's not necessarily you are using ARCS model. You can also use NURBS or NARMA or NARMAX model. or higher order or more complicated models. Okay, so you're going to have all these 100 pairs of A1 and B1. Therefore, you're going to do your prediction, isn't it? You're going to predict, then you're going to have 100 predicted value of y predicted. Okay, you're going to have hundreds of them, 100 predicted prediction of y. Okay, so from 100 prediction, of course, you're going to have 100 error. Of course, this is also related to your data, isn't it? Or prediction of y is 100 due to the pair. But if you have 1,000 data, okay, I forgot about it. You're going to have the prediction with more data. Let's say one data, you're going to have input and output y is 1,000 data. So what you're going to do, you're going to put all that values, okay? So you're going to have u, and then you're going to have your parameter b over a. And then if you have 1,000 u and 1,000 y, of course, you're going to have 1,000 predicted output, okay? But that is using the first pair. And then you have 100 pair. So you're going to have 100 predicted output with 1,000 data each. So from that 1,000 data, you're going to get one error, which is mean square error. You're going to have 1,000 error as well, isn't it? So please don't forget about this. So the error will be the actual y minus the predicted y. So in this case, you're going to have 1,000 predicted error as well. Okay, so but from that 1,000 predicted error, you're going to find one error, which is the only one mean squared error, okay, for each pair. Each pair of A1 and B1. So how many pair do you have? 100 pair. So this thing will be repeated in a loop 100 times. Okay, so within your 4 loops, this is your 4 loops, you will do your calculations of your using your error, using your pair that you generated using GA. You will substitute into these equations of ARC's equation here, substitute that into that equation, and then calculate the predicted output, okay, and then calculate your predicted error, and then from that predicted error you will get one mean square error for each pair, and then you have 100 pair, and that is only for one generation of GA. Okay, then with this 100 pair of mean square error, you will evaluate which one is performing the best. You will then do the selections and rank them. So it looks very complicated, isn't it? But somebody have actually come up with the toolbox, and the toolbox is available. You can use it. But this is what happened within the toolbox. Okay, so with that 1,000, with that 100 pair, you're going to get from that 100 pair, you're going to evaluate the best. Okay, evaluate the best mean square error. And then that will be your plot. You can plot that, okay, and then plot the best for one generation. Then you're going to create many generations. So at the end of the day, you will see that your generation, let's say I put generation means a cycle, okay, one cycle you have one time. Oh, of course, I forgot. Then before you evaluate this, before you go for the next generation, let me cancel that first. Before you go to do your next generation, you need to create new population, isn't it? So creating new population, you need to use your crossover, and then you do your mutation. Okay, so you will create new population. Then that new population will be brought to the next the next cycle. You use the new population to calculate your new performance, okay, the new performance, and then from there you can get your new predicted output and new predicted error, and then from there you will get one mean square error, okay, from that one pair. So if you have 100 pair, you're going to have 100 mean square error. So from that 100 mean square error, you will then plot the best mean square error, because that is actually the achievement of your one generation. Then you're going to go for the next generation, and on and on. until you converge. Okay, so then you actually repeat this loop over and over again until you converge. So normally conversion of GA will looks like this. This is the number of generation, and this is your cost function. In this case, is a mean square of error. Of course, you're not going to plot all 100 mean square error. You're going to find the best mean square error for each generation. Okay, so then your system will start to find the best mean square error, and every time, maybe sometimes it actually stuck at one value as if it's already converged, but because you have mutation and you have crossover, that mutation and crossover will allow you to change. Okay, it will allow you to move from one search area to another search area, and then it actually will allow you to converge to a better value. And then maybe after sometimes you start to converge into this value, but because you have mutation, maybe that is not the minimum that you can get, and then you will actually converge again to a different value. And sometimes when you start to converge, though doesn't change anymore, maybe you already reach the best performance, and from there you can stop your genetic algorithms. Okay, and then you can find what is the pair of A and B that is actually obtained at that generation. Let's say you stop at generation 50, for example, and then you can go back to your computer, your programs. You can actually select this at that generation. What is the performance? What is the best performance? You find out that, oh, this mean squared error is actually coming from a pair of A1 and B1. Therefore, this is the best performance for your algorithm, the best parameter for your algorithm. All right, so that's how you do it. So you can actually do this for any optimization, not just parameter of A and B. Okay, you can do this to optimize the value of KP. Like you see later on, I put in the video, recorded video of self-tuning PID, where the PID is self-tuned, but actually GA will do that also. GA able to tune PID to get the best performance PID as well. Only thing is that GA is a bit slow, so it cannot actually perform fast enough previously, but now of course it can perform very fast. All right, okay, so this is how GA is being utilized in terms of putting it into your program. So for you to do the programming, you need to initialize what are the mathematics that you need to do. Okay, in this case, for example, you want to do optimization of parameter estimation for arcs. Okay, so you come up with the equation of arcs and create what are the parameter that need to be estimated. So then you have this parameter, and then find out the range of the parameter that you want to estimate. These are the range. If you don't have range, you need to define range. Okay, and then decide on the number of your population. So normally number of population is depend on your search area. So if your range is really big, then you want your population to be more. If your range is small, then you do not need to have too much population. Then your system is said to be overpopulated. For example, I want to search my missing handphone. Let's say my handphone is missing. It is ringing, but the sound is too slow. I cannot hear it. So I want to search all by myself in my house. I cannot do it because I cannot find it. It is ringing, but I cannot hear it. All right. So if I search alone, it will take me one whole day. So what I did is that I call upon all my neighbors, come to my house and do the searching. If I call in my house, maybe I can accommodate 20 people. If I go more than 20 people, it will be too overcrowded. Okay, so overcrowded will create noise, isn't it? When you create noises, your search will not be very good anymore. Okay, because you cannot hear even your sound of the phone. Okay, so in reality, in programming, is also the same. When you are overpopulated, your calculation will have some error because you will calculate the same thing over and over again, and you might replicate the same calculation over and over again on the same thing. So you don't want that. Okay. So population, there's a rough estimation on what is the best population. So look at your search area. If I call the whole neighborhood, maybe 100 people to be in my home is too much. Okay, too many. So I don't want that. Okay, so look at the search area. What are the biggest search area? If it's really big, then your population should be also quite big. Okay, so otherwise the maximum you can go, maybe 100 is enough. So you must remember also your computational effort, because if your computational effort is going to be really big, isn't it? Because you're going to create 100 chromosomes with binary numbers, and then you're going to evaluate them simultaneously. Okay, you're going to evaluate the performance simultaneously by putting it into this value here. By putting back the binary numbers, convert into decimal numbers, convert into real number where you get 100 pairs of A1 and B1, and then use that 100 pair, put back into your problem and evaluate the performance. In this case, it's ARC's problem. So then the complexity comes with the data as well. So if each and one of them is having 1,000 data, you have 1,000 input and 1,000 output, you're going to put your ARCS model in the format of your similar to your your y equals to phi multiplied by beta, isn't it? Similar to least squared punya features, isn't it? Punya function, isn't it? Then because from there you can easily calculate using matrix, isn't it? So you do that, and then you predict your y output predicted, and then from the predicted output you get your error, and then from the error you will get 1,000 error, of course, because every cycle of data. So inside here there's a for loop as well for you to calculate the data. So there are 2 for loops here, okay? So once you have evaluated the performance of your predicted output error, you get your mean square error, and then for each pair, so you have 100 pair, remember? So you're going to evaluate all 100 pairs simultaneously. You're going to have 100 pair or 100 mean square error. So from 100 mean square error, you're going to find out what is the best mean square error, and then you're going to plot the graph of your performance graph using the best mean square error. Then after that, it doesn't stop there. You're going to then do the crossover and do the mutation. And the moment you do your crossover and mutation, you are creating a new population. Based on the new population, you will go for the next generation. The next generation will do this process all over again, and then you will then you will actually end the loop as soon as you has converged without any changes anymore. You can put features that if loop there to end it. Okay, you can end the generation if the value of your mean square error doesn't change anymore. Okay, so if it doesn't change after 100 generation, for example, then you can stop. So this is the generation can be also quite high. You can have maybe 500 generations. Okay, so if it doesn't converge anymore, then you might want to have a stopping criteria there, so that the algorithm will stop the moment it start to converge. Okay, so because sometimes when it's already converged and doesn't change anymore, even if you set the mutation rate higher and the crossover rate higher, you're creating new features, okay, still it will not converge, means you are already reaching the maximum or the best performance for your algorithms. Okay, so that is giving you your best parameter. So from that you can trace back what is your best parameter obtained from this exercise. So that best parameter is the parameter for your ARCS model. All right, is that okay? Does it make sense or not? Do you understand or not what I mentioned? Can you hear me? Faham tak ni? Senyap je semua orang ni, risau saja. Abrar, are you okay? Does this make sense or not? Ni ada ke tidak ni, semua orang ni dengan tidur ni, I think. Faiz, are you there? Ada pun. Arif je ada.
Ada.
Ada kat mana? Boleh berlari. Oh, that's make sense. Apa? Tapi kita dapat ulang semua untuk lebih faham. Okay. Tengah memahami. Alright. Okay, so this is how GA works out. Okay, I don't have any more things to share with GA. So for your test or for your examination about GA, I will ask on the concept. Of course, I will not ask you to generate all the estimation and whatnot. Is too complicated. So normally I will ask on the concept of GA. For example, the apa ni the this there was a past year questions asking about, please describe this procedure, the process of GA according to this structure. Okay, what happened during the population setting, what happened during the mutation and crossover, those are the questions that can be asked. So we cannot ask you so much on the mathematics because it's too comprehensive, too complicated. And there are also past year questions on GA asking you to explain how to utilize genetic algorithm for parameter estimation of ARCS model, like what I explained just now. So that's why I explained that just now. Okay, so this is the kind of things that you will ask using GA. I hope I can show you the MATLAB programmings, but basically this is similar to what I have explained just now. Okay, so still we cannot write the overall MATLAB programming because it requires us to use a lot of functions in the MATLAB, okay, in the toolbox, so it's not very possible for me to show you step by step. Okay, is that all right? So I think I'm going to stop about GA. I want to start on neural network, but I think it's a bit too late, so maybe I will start neural network tomorrow